So, good afternoon, dear students, and welcome to our lecture today. Today, we're going to talk about compressible flows. So, compressible flows is now a completely new topic. It's very different from what we have done so far, where we exclusively talked about incompressible flows. So, what is the idea of what we will be doing today? Let me show you maybe the first slide of today, title slide. You see here a typical picture of an experimental study. You see probably a bullet or a bullet-shaped object flying from left to right through the test section. And you see in this gray shading, you see these structures like these lanes going diagonally through the pictures in all different directions. These are shock structures. Shock structures. Maybe you heard about the sonic boom when you have supersonic airplanes. These are all typical structures, typical phenomena you only have in compressible flow. And we're going to ask the question today: what is compressible flow? In what sense does it differ from incompressible flow? What novel phenomena do we have? Like these shocks, what else do we have? What do we need to consider? And then we're also going to try to find out when it is necessary to consider these effects and when it will be safe to completely neglect these effects. And you will find that for you as biomedical engineers, there will be very few occasions where you actually need to look into compressible flow. Most things that biomedical engineers have to deal with are incompressible. Nevertheless, for completeness sake, because compressibility is an important phenomenon, we're going to have this lecture, and you will see it's a beautiful sub field of fluid mechanics. Okay, so maybe before I start with the actual topic of today, we'll quickly look at the schedule. Today will be the last formal lecture that we have. Next 2 weeks, we're going to have our lectures on experimental fluid mechanics and computational fluid mechanics. The idea was originally that we would go and visit the wind tunnel in Zurich for the experimental fluid dynamics, but obviously this is not possible in the current situation. So, well, to be honest, I don't know yet exactly what we're going to do next week, but probably I will do just a formal lecture. We're going to look at a few methodologies in experimental fluid mechanics. Then in 2 weeks, we're going to do computational fluid dynamics, where we're going to do a little workshop together, work on a few tutorials on a CFD solver, trying to give you a bit of an idea of how to deal with these codes, trying to show you where problems may be, what to do, what not to do, and to look at a few results. So this is just a little outlook for the coming 2 weeks of this course. But now back into the topic of compressible flows. So this is what we're going to do today. We're first going to list a few basic assumptions, mainly assumptions for today's lecture. We're going to look at a few thermodynamic relations. We're going to define the Mach number. So thermodynamics is a field closely, let's say, related to fluid dynamics, and compressible flow is where the two fields, thermodynamics and fluid dynamics, are starting to overlap. Okay, so we're not going to do thermodynamics, but we're going to look a little bit at some relations we need to understand the flow. Then we're going to define conservation laws, essentially the same conservation laws as we had in incompressible flows, just adapted for the new phenomenon. And specifically, we're going to look at one application, and this is the flow in a nozzle, because it combines a lot of very nice phenomena and also is of practical relevance. And in this flow through a nozzle, we will find conditions where shocks are developing. So we're going to look at shocks, at normal shocks first, And then toward the end of the lecture, we're going to generalize that into oblique shocks, detached shocks, and we're going to end up with a phenomenon known as Prandtl-Meyer expansion. So this is the program for today. Let us start with basic assumptions. So what are basic assumptions for today, only for today? We're going to assume that we always deal with a perfect gas. Perfect gas, this is something which, well, perfect gas is a gas which is described by this equation, P pressure divided by density rho equals R times T. R is a specific gas constant. That's a constant you can look up in tables for every gas, and T is obviously the temperature. So it says that the ratio between pressure and density is proportional to temperature. You increase temperature, the ratio P over rho goes up and vice versa. Gases that adhere to this law are called perfect gases. Air is in a certain range. If it's not too cold, not too hot, the pressure not too high, not too low, air is well described by a perfect gas. Many gases are that. As soon as you come to a range where you have start to undergo phase changes, like in the atmosphere when you have condensation, or even in formation of ice, or when you're so fast, like in a re-entry vehicle from space, when you have a dissociation of the gases, so you get a plasma with ions, then the perfect gas law is not valid anymore. But for most applications, it's actually pretty good law. Today, we're going to restrict ourselves to one-dimensional flows. So we're only going to, or let's say quasi one-dimensional flows, we're going to look only at flows along a streamline. We're not going to deal with real 2D or 3D structures. We're going to neglect any unsteady effect today. So we're just dealing with stationary flow. du dt will always be zero by definition. And we're going to neglect viscosity. You know from the past lectures that viscosity is quite an important phenomenon. Today we're going to neglect it because, well, things will be complicated enough without viscosity already. Same goes for gravitation. We're not going to need it. And the third thing, or the final thing is we're going to consider adiabatic flow. So adiabatic flow means there's no exchange with energy with the outside. So the flows that we're considering are always closed systems. There's no transfer of heat or mass with the surroundings. Okay, these are just a few basic assumptions that we're going to use today. Flows that behave like that, especially when they're inviscid, are so-called isentropic flows. And I'm going to come back to that, what isentropic means, but it will be very helpful in the following derivations because we're going to consider the value entropy, which is a thermodynamic quantity, as a constant. Okay, let me go on after these basic assumptions to a few basic thermodynamic relations. If we have a perfect gas, we can define energies of the gas. First, an inner energy. I apologize that the slides are in German, but I trust you can deal with that. The inner energy of a gas, or let's say the energy density of the gas, is denoted by the variable E, and it's proportional to the temperature. I think that's quite intuitively clear. If we rise the temperature, the inner energy goes up, and the proportionality constant is called CV. And this is just a constant. Again, you can look it up in books, what it is for air, what it is for other gases. The second line on this slide, or the second formula on this slide, is the differential form of that. And we're going to use quite a lot this differential form or other differential forms in the following. So let me do something on a blackboard to just explain to you what this really means. So I'm going to switch back. blackboard now, so we can take a look at this. So let us assume that we have a reservoir which is filled with a gas, for instance, with air. And this reservoir is tightly closed by a lid such that the volume inside this reservoir is constant. Right? And if we have a temperature inside this reservoir, temperature T, we're going to compute the energy, the inner energy, as CV times T, right? That's essentially what it said on the slide before. Now, if we increase the temperature, and if we just increase it just by a little bit, let's say by a delta T, or let's say by an infinitesimally small temperature dT, then the energy will increase by just a little amount, E plus dE CVT plus CV dt. I think this should be quite clear, especially because it's a linear relation. Then this infinitesimally increase in inner energy is equal to CV times the infinitesimal increase in temperature. So dE equals to CV dt. We're going to work a lot with this infinitesimal increases in a quantity. So just think of this as a delta T. A very, very small delta T leads to a very, very small increase in energy of delta T. Okay, so much for the inner energy. There is a second, well, actually, I'm not going to go back to the slides. You can look it up yourself. There's a second quantity on this slide, which is called the enthalpy. Here is the inner energy E. And here's the enthalpy, which is typically denoted by a H. Okay. Now, if we take this example with the bucket, the situation looks a bit different for the enthalpy. Again, we have a bucket, but this time we're not putting a lid on top of it that seals it tightly. We're putting a lid in it that can slide up and down. We're going to put a weight on top of that lid such that it exerts a pressure onto the fluid volume inside. So instead of having a constant volume as here, we have inside a constant pressure, right? So it's not the same situation. Here the volume will remain constant, and in this setting, the pressure will remain constant. If we heat up this volume by an infinitesimal amount dt, what will happen? Well, if we increase the temperature, the pressure increases, right? And the whole lid will move up a little bit, okay? So by moving the lid up a little bit, there's an additional bit of work that is being done, right? And that work is related to the increase in volume times the pressure, right? That's the power or the work that we're doing. And of course, the increase in volume will decrease the density. Yeah? And this effect, so the increase in inner energy just by increasing the temperature plus the mechanical work done is contained in the enthalpy. So the enthalpy is defined as E plus P over rho. So the inner energy plus this here, this term P over rho, which is related to the work that is being done here, and can also be shown that this is again proportional to the energy. So proportional to temperature. We already know that the inner energy E is proportional to temperature, and the perfect gas law tells us that P over rho is also proportional to temperature. So the sum of the two must also be proportional to temperature, and it's commonly known as Cp over T. Note that we have two different constants. Here we have Cp, and here we have Cv. V indicates that we're dealing with constant volume, and P indicates that we're dealing with constant pressure. Likewise, we have a pH equals Cp. So these are the two forms for the enthalpy, and these are the two forms with the differential form for the inner energy. And of course, you can relate Cv and Cp. We can use the specific gas constant R that we defined from the perfect gas law. Let me write it down again. Equals RT. This is the perfect gas law. You immediately see P over rho is equal to RT. So this is RT, this is CVT. So obviously Cp must be Cv plus R. So all these quantities are related, and that's exactly what we see here on this slide. See all these different ways of writing the enthalpy in terms of temperature, in terms of P over rho by itself, and so on. So these are all, well, it's a lot of formulas, and that's a bit the nature of compressible flows. So I personally find it difficult to remember all these formulas by heart. So it's good to have a good book or a good set of slides with all these formulas ready. So on the following slide, we have just some more information on that, like what I just said before. The difference between Cp and Cv is just equal to R. We just saw this on the blackboard. What is also commonly used is the ratio between Cp and Cv, which is called gamma. Just a definition. There's no magic to that. It's just a definition. It's also easy to remember. It's 1.4 for air. Yes, you can compute Cp, you can compute Cv, and so on. I'm not going to dwell on that. These are just really numbers to look up, formulas to look up whenever you need them. Now, the third slide, this is this whole story about this entropy. I already said this in the very beginning. So what is entropy? Entropy is an additional physical quantity. It's something like an energy or an enthalpy or an inner energy. It's just a quantity which describes the state of a gas. We can understand it a little bit as a measure of chaos, as a measure of disorder. You can relate it in information theory to the amount of information contained in a gas configuration, right? It relates to the number of possible configurations a gas can take. Apart from that, it's just an abstract quantity which is defined as shown here in this line. As I said, we're gonna only, let's say, remotely use entropy today, in that we're gonna say entropy will remain constant as an idealization in all our processes. Because whenever you can say that entropy must remain constant, you can use these relations and come up with the formulas or the relations I have here boxed on the bottom of these slides. So these are relations for isentropic processes. So in general, you can say whenever you have a process that is adiabatic and inviscid, you will have an isentropic process. There's one exception, but we'll come to that at the end. So that means you can take a gas and it can change temperature and density will change or pressure will change, and all of these are related. And as long as the entropy, the overall entropy does not change, these relations hold. So like the first formula here, which relates the pressure to the density. So if you know the pressure and the density in a reference state, P ref, rho ref, then you can compute what the pressure in a modified system will be if you know the density. These two are related through these expressions. And you see here, you have an exponent gamma. This is 1.4 for air. So these relations make our life a lot simpler. We know that pressure is directly related to density, or in the second formula, pressure is directly related to temperature, or finally, the third formula, density is directly related to temperature, as long as a process is isentropic, which we're going to assume. Okay, so we're nearly through with our basic relations, with our basic thermodynamical relations. We have now the perfect gas law. We have defined these energies, inner energy, enthalpy, and we have defined these isentropic relations. There's one thing missing, and this actually turns out to be a very central thing, and it's the speed of sound. And that's what we have on this slide here. Compressibility is inherently tied to the propagation of sound waves. Only if you assume that a medium, a gas, is compressible, you can get waves propagating. In incompressible flows, what we have done so far, there's no way you can get acoustic waves. Acoustic waves, the wave phenomenon, absolutely requires compressibility. And you can do a detailed analysis, and you can look this up in books. For instance, the Kuhn and Cohen book has a nice chapter on that. And you can find out that if you have small variations in pressure and related to that, because it's isentropic related to that, you also have small changes in density, you can compute the wave speed, so the propagation speed of these waves. And the first formula on this slide describes exactly what this wave speed is. So A is typically used as a variable for the speed of sound, or the wave speed of sound waves. So A squared is equal to the partial derivative of pressure with respect to density in an isentropic process. dP d rho, as long as S is constant. We can use our isentropic relations. I switched one slide back. Look here, the first formula relates P as a function of rho. So you can actually use this formula to take the derivative, the partial dP d rho. You can use this formula, and if you do a bit of algebra, you will end up with these expressions down here. For a perfect gas, following these isentropic relations from the slide before, the speed of sound is given by the square root of gamma, this ratio Cp over Cv, times R, specific gas constant, times temperature. Or you can replace RT by P over rho, that comes from the perfect gas law. So we now have explicit formulas for the speed of sound in a gas. And you can see that if the temperature increases, the speed of sound will increase. Sound waves will go faster. If pressure increases and density remains constant, we'll do that, and vice versa. If density increases and pressure remains constant, it goes down. You can also relate it to the enthalpy of a gas. So changing the enthalpy of a gas will also change the speed of sound. Okay, so the speed of sound is not just a given constant. It's not like the speed of light or something like that. It's really a quantity that is changing with the current state of the fluid, how warm it is, how dense it is, under how much pressure it is. Speed of sound will constantly change. So also in the atmosphere, if you go up in the atmosphere to very high altitudes, the speed of sound will typically decrease. There's a final definition I need to make here, and that is the one you have on the bottom of this slide. You know that fluid dynamicists love non-dimensional numbers. And of course, also compressible flow has its own non-dimensional number, and it's called the Mach number. I'm sure you have heard about the Mach number. The Mach number relates the velocity of a fluid, or velocity of an object in a fluid at rest, relates this velocity to the local speed of sound. If it's below 1, if Mach is below 1, we're obviously slower than the speed of sound. If it's above 1, we're faster than the speed of sound. And we're calling it supersonic flows. Because I think it's important that you hear all these terms, put this description quickly on the blackboard. So you just have the full nomenclature of different Mach numbers. So for a Mach number, which is less than 1, we're talking about subsonic flows. If it becomes larger than 1, we're talking about supersonic. I'm sure you have heard these terms before. If it is at 1, or let's say close to 1, because in reality, if something is close to 1, there will be regions where it's slightly above and regions where it's slightly below. So if it's somewhere around 1, we're typically talking about transonic flows. Okay. So this is the classical terminology for subsonic, supersonic, transonic flows. In the extreme case, for very, very high Mach numbers, so this is, for instance, what you have in re-entry vehicles, satellites, or let's say a space shuttle that comes back into the atmosphere very fast, rather low speed of sound out there, so you get very, very high Mach numbers. The Mach numbers are higher than 3. In other books, you might find higher than 5, but just somewhere, let's say, where Mach number gets really high, we're talking about hypersonic conditions or hypersonic flows. Why do we need a special term for that? Well, in these situations, you usually, or you can get dissociation of molecules. So molecules fall apart and you get ions and you get a plasma. So you get this shiny glow when a satellite re-enters the atmosphere, and the physics starts to change. Perfect gas law is no longer a valid assumption. So this is why we're talking about hypersonic fluid, separate theory. There's one line I'm left open up here, and that is the condition of Mach equals 0. And Mach equals 0 is what we have done so far. Mach equals 0 is the condition of incompressible flow. And of course, well, Mach is U divided by A. Mach 0, well, it could mean that U is 0, and then of course, well, U 0, we have no flow at all. It's of course not very interesting. No, Mach 0 actually corresponds to the case where we assume that the speed of sound tends toward infinity compared to the flow velocity. So incompressible flow, in the language of compressible flows, actually means that we have a flow where the speed of sound is so fast that every information is propagated at infinite wave speed. So all information is immediately everywhere, and then we have incompressible flow. Wherever we have finite speed of sound, we are either in subsonic or in supersonic or hypersonic flow conditions. So we are, or what we did the last 10 weeks was just up here, Mach 0, or let's say at least close enough to 0 so that we can consider compressibility to be irrelevant. We're gonna get a bit of a better boundary on that later on in a few minutes. We're gonna talk about at what, below which Mach number we can forget about compressibility. So that is the Mach number. And with that, we have essentially understood everything, or we have defined everything that we need to start a conservation loss, because that's now the next thing we need to define. And as usual, as what we did in incompressible flows, we start with the conservation law, which is the most straightforward, and that is the conservation of mass. And you will see it looks almost the same as what it did for incompressible flows. That was, I think, 8 weeks ago. Again, we got to look at a bunch of streamlines going through, let's say, at least virtually through a pipe. So we have streamlines here. And so on. We have all these streamlines here, and we have cross sections. Maybe let me mark that color. We have here a cross section A. And if we mark here a local coordinate x, a, of course, is a function of x. And at the same time, we'll have a velocity here, u of x, u of x, and we also have a density of the fluid, rho of x. And if we multiply the three, so A times U, that gives us the volume flow rate. And if we multiply this by rho, we get a mass flow rate. So how many kilograms of the gas are flowing through this cross-section A per time unit. I'm calling this by m dot mass flow rate as the units kilograms per second. And I think it should be intuitively clear that the mass flow rate should be a constant, right? We should not lose any mass. Whether we're in this cross-section, or the other cross-section, or any cross-section for that matter, the mass flow rate should always be the same. So in some way, or not in some way, this is actually the law of mass conservation. And the only difference to incompressible flows is that we're now keeping the rho here because rho can also change. I would like to make one variation to that because, well, this is a nice formulation, it's intuitively clear, but later on, we're going to work a lot with these differential formulations, differential forms, and I would like to derive that quickly. And well, even though it looks a bit abstract in the beginning, I can tell you it gives you, I would say, more insight into well, what is going on. So let us take this formula here and let's form the total derivative. So we are trying to understand what an infinitesimal change of the mass flow rate can look like. An infinitesimal change of the mass flow rate, so it's the total derivative of this formula, is given by d m dot d rho times d rho plus dm dot dA times dA plus dm dot du times du. And well, we can actually evaluate these differentials, right? We can just say what dm d rho is. So dm dot equals dm dot d rho. So d rho of this expression is just A times U times d rho plus dm dot dA is just rho times U times dA plus dm du is just rho A times du. Put this down. Okay. So this is now the total derivative of dm dot. So if we change the density by a little d rho or a delta rho, if you like, we have to multiply it by AU and we get the change in mass flow rate. Or if we change the cross section a little bit, we have to multiply this little change by rho U and we get the change in mass flow rate, and so on. Now, what have we said before? The mass flow rate should always be constant. So that means the conservation law actually says the infinitesimal change in mass flow rate should be zero, right? That's what mass conservation says. We should not have a change. So the sum of these three terms should always be zero. That's just another formulation of the law of mass conservation, that the sum of these three terms must always be zero. And we can rewrite this in a nicer form by dividing, now you can still see it, by dividing this whole equation by rho A U. And if we divide each one of these three terms by rho AU, we see the first term, the AU cancels, and we just maintain a 1 over rho. So for the first term, we just have it be rho divided by rho, right? That's the only thing that remains. From the second term, rho U cancels, and the only thing that remains is a dA over A. And for the third term, it's only a du over U equals 0. Okay, so we're at the end now. This is the differential form of the mass conservation. It tells us that the sum of these three terms must always be zero. And now let's try to understand what these terms mean. What is the U over U? Think of the delta U. So if you have a little change in velocity and you divide it by the current velocity, that's something like a relative change, right? It's like if you have a velocity of, let's say, 10 meters per second, you increase it to 11 meters per second, then the du would be the change, like 1 meter per second divided by 10, so it's 10% change. So it's like a 10% change in velocity must be compensated, let's say, by a 10% in decrease by cross-section, or by a 10% decrease in density, or by the combination of it. So the percentual changes, or the normalized changes, the relative changes of any of these quantities in their sum must always be zero. So even though this expression might look, well, quite confusing in the beginning, I think the insight we can gain from these expressions is even better than what we have up here in the more classical form of mass conservation. The sum of relative changes in rho A and U must add up to zero. And this is the law of mass conservation. Let me switch back to the slides. So we have here conservation of mass, not in the referential form, but in the form we had in the beginning. The second conservation law is conservation of momentum. And I hope you can recognize some terms you saw in the Navier-Stokes equation. On the left-hand side, we usually had the du dt. That one drops out because we're studying only steady flows. We're not considering changes in time. So what remains is the nonlinear term, u du dx. That's the only term that remains because we're only looking at one-dimensional flows. We don't have the v and the w. Okay, so u du dx. This side here looks almost the same as Navier-Stokes with a few terms kicked out. On the right-hand side, we have the pressure gradient in x, dP dx. We divide by rho because in this form, the rho is taken from the right-hand side to the left-hand side. In the classical Navier-Stokes equation, we had here, in addition, on the right-hand side, had the viscous term, but I told you today we're neglecting viscosity. So that is really what remains of the Navier-Stokes equation. It is also known as the Euler equation. Relates pressure on the right-hand side or pressure gradient on the right-hand side to velocity or velocity increase. In incompressible flows, we were done with these two equations. Now, in compressible flows, we need additional equations, and that is the conservation of energy. And for the conservation of energy, we take the enthalpy H, and add something which looks like kinetic energy, or reduce the kinetic energy to it, and that should remain constant. Or we can replace H by CPT, and that should be constant. So this is the third equation that we need. And in addition, just for completeness sake, I also listed the perfect gas law, which relates the different quantities with each other. So this is a set of equations that we need for understanding compressible flows. Let me, before we go to the break, just derive one applied result, which should give you, I hope, a deeper understanding of what we can do with these equations. And that is the situation for a reservoir with a gas in it, and it's under a certain pressure, and we puncture a hole in it, and then the gas flows out. And we assume that outside the pressure is really low, or we can, let's say, virtually think we're doing this in outer space where the pressure essentially is virtually zero, and we're going to compute how fast the gas is flowing out. So let me do this on the blackboard. Just takes a few minutes, and then we're going to take a break. Okay. Let's stop here. So let us consider a large reservoir with a little opening here. And in this reservoir, obviously, we have a velocity u0, and the gas has a state we call the stagnation state, because everything is stagnant. And the stagnation state is typically denoted by an index 0, rho naught, P naught, T naught. This is the stagnation state of the gas when it's at rest. In German, this is called the Kesselzustand. If we puncture a hole in here, gas will flow out. It will flow out at a certain velocity u, which is non-zero, obviously. And it will flow out into the outer atmosphere with properties P, rho, and T. So we'll change from the stagnation state to this state. And by changing from this state to this state, it will also change its velocity. And we're going to find out what this velocity is. So energy conservation tells us that Cp times T plus U squared half is constant. Right? This is the law of energy conservation. For this configuration, this means that the energy here must be equal to the energy in this state. So what is the energy in this state here? Well, it's Cp times T naught plus U squared half. Well, but here the velocity is 0, so this term is 0. So the energy here, the energy in the reservoir is just Cp T naught. It's just the enthalpy. Down here, we have obviously Cpt plus U squared over 2. So this is the energy in this state here. Now let's go to an extreme case. Let's say the pressure P is almost 0. Or if we go to space, it actually, well, it tends very much to 0. From the perfect gas law, we know that if the pressure goes to 0, also the temperature will go to 0. And if the temperature goes to 0 out here, obviously U must become larger. It will go to a maximum possible velocity. So U will tend toward a U max. And this U max is related to the stagnation state Cp T naught equals here, oops, you can see this. This is 0, so it's just this term. It's U max squared over 2, or you can say U max is equal to, we just solved this equation for U max, it's equal to 2 Cp T naught, or we can also write just using the relations from a few slides back, we can also express this in terms of the speed of sound. It's like 2 over gamma minus 1 square root times A. I hope you can, yeah, you can see the A here. This is the speed of sound here. So there is a maximum velocity to which the fluid can accelerate. It cannot go any faster than this U max for a given energy contained in the reservoir. This energy is defined by rho naught P naught T naught. So for the example of atmospheric of air at atmospheric conditions, so let's say you have air at atmospheric conditions, you put it in a big reservoir, put it in a rocket, put it in space, and make a hole in it, the fluid will accelerate and flow out. And it will take all the energy and use it for accelerating the fluid. But this energy is just sufficient to accelerate it up to this maximum velocity. If you plug in here the values for air, you will see that you cannot accelerate, can accelerate air only up to 750 meters per second. If you use the stagnation state. Of course, if you put more energy and if you put a rocket engine to it, then it can of course accelerate more. But just using all the energy that's contained in ambient air, we can accelerate maximum up to 750 meters per second. You can plug in the numbers here and that's what it can. Okay, so this is the first application of our conservation laws. So let's take a break now until 20 past and then we'll continue with this application and look a bit more in detail what goes on. Okay, so I'll see you again at 20 past.